Stefano Alberto Russo is going to talk about science platform implementations, the microservice-oriented ones.
So, hi everyone, I'm Stefano Alberto Russo. I'm a researcher at INAF, and in particular in the Observatory of Trieste. I'm going to talk to you about microservice-oriented science platform architectures. And this is a project which is undertaken under the ESCAPE European project. And so let's see what are we going to talk about. So first of all, what is a science platform? Interestingly, there is no unified definition, even if anyone is talking about it. To us at INAF, at ESCAPE, a science platform is an environment which is designed to offer users a smoother experience when they interact with the data and computing resources, and possibly in bringing the user to the data and not vice versa. We usually assume a web browser in the role, so web-based applications like Jupyter, we all know it very good. We also can assume other kind of notebooks like R notebooks, for example, but they are all web-based, so there's always a web browser in between the user and the science platform. Other approaches can be also used. For example, if we talk about interactive desktop, there's no reason why we shouldn't classify a science platform as something which provides a remote VNC desktop to the users. Now, if we take the LSST science platform definition from the science platform design document, I think it's pretty spot on. And it states that a science platform, it is a web portal which is designed to provide essential data access and visualization through a simple-to-use website, then a notebook environment that will provide notebook-like interfaces. And in this case, they also stated that this is based on Jupyter Lab. And importantly, they also stated that they enable next to the data analysis. So you don't bring the data to the user, you bring the user to the data on the science platform. I think this is a very good definition. And there are a lot of science platforms which falls under this definition around. So here are some examples. For example, in the public research and academia, we have CERN-1, we have ESA Data Labs, we have the LSST science platform, which is going to be developed. We have a lot of them. In the private sector, in particular in research and IT industry, we have also a lot of platforms that can be classified as science platforms. We have Google Colabs, for example, which is entirely based on notebooks. Kaggle kernels, same thing. And Azure Machine Learning Studio, it's similar, but also provides facilities for moving the data and staging the data around. So apparently, the color of the science platforms is blue, as you may notice on the examples on the right. But all of them, they kind of have strong limitations. They have strong limitations because a user usually cannot run in an environment which is not supported by the platform. And this can range from just a different Python version to wanting to use a different Linux distribution. A user also cannot change the interface for using the science platform itself. So if the science platform is going to provide web-based access, like Jupyter or similar, you cannot run native graphical user interface applications, which are, by the way, common in astrophysics, for the reason which we just saw in the previous talk, by the way. It is also required to support all the software from the administrators and also all the versions, which from an administrative point of view, this might be a very, very strong overhead. So can we do something better? Here is where microservices jump in. Microservices are independent and self-contained units which can perform different tasks, but well-defined tasks. They can range from just summing into numbers to run very complex neural networks. They are actually already very commonly used as building blocks. So all the science platforms we see out there, they use they use microservices for DevOps. But they don't really use microservices for the user tasks. So what about using the microservices not only for the DevOps, not only for the building blocks of the science platform, but for the user task itself? When we need to talk with a microservice, we need to use an interface. This is how they interact each other in the science platform itself. The interfaces can be of different kinds. Some examples are REST APIs, which are pretty common, but just simple HTTP is also a choice. SSH, it is also another possible interface. If you just run commands from one microservice to the other, or from a user to a microservice using SSH, it's a pretty viable interface. And you can also use more older school approaches as a remote procedure call, for example. I think that the also important thing is that if you want to use microservices, they naturally fit with the containerization approach, because it's quite straightforward that every microservice, it is a well-defined container. And once a microservice, it is containerized, it is completely unaware about the computing resource where it is running, and in general, the entire computing infrastructure, which makes it extremely portable. Only the interface which is used to interact with the microservice is relevant. We consider only TCP IP-based interfaces, and this is because they are way easier to route across the modern internet. So this is the architecture we propose. On the right, we have a big yellow block, which is the science platform itself here. We have a web application, which is used by the user to interact with all the science platform. We have a container registry, a share file system, and then on the left part, we have the computing elements. Here we just show a single computing element as an example. So the science platform interacts with the computing element using an agent, which is capable of interacting with other external components like container registries, for example, just Docker Hub. The computing element is then running the microservice container, which is in turn talking back with the science platform and the user. Now, how does this work? First of all, the user interacts with the web application. It asks to the web application to submit a task. The web application talks with the scheduler of the science platform, which sends out the agent on the computing element assigned to the user. The agents download the microservice container, either from the internal container registry or from the external container registries. And at this point, the backward tunnel from the microservice container to the user is established. In this way, the user talks with its own microservice. The user is completely unaware about the entire orchestration here. But if the task of the user is doing something on, let's say, port 8080 or 8888 as a Jupyter notebook, the user only needs to know that the microservice for his task will be available on this specific port and access through the platform. I would like to stress that if we use this approach, this is actually something that does not prevent to use what it is already done. In fact, Jupyter itself can be used as a microservice, and it is used as a microservice in the vast majority of the science platforms. The point is that the user has no control of what microservices are run by the platform. So we can do more. We built a prototype at INAF to explore all this. And here it is a concrete example on how you use this approach to run the standard Jupyter notebook application. So on the left, we have a task, which is running a container, which is called Jupyter notebook. We have a container image here, which is Jupyter/base notebook. And this is the official image of the Jupyter notebook container, which is pulled down from the Docker Hub. So when I submitted this task to the science platform, the agent on my dedicated computing resource, actually on my allocated computer resource, pulled down the image from Docker Hub. I didn't even have to upload anything to the science platform. I just set up the container to use what I wanted. At this point, the tunnel port is 7002, and this is connecting to the microservice port 8888. So as a user, I'm connecting to the Science platform on port 7002. And this is letting me to directly talk with my microservice on port 8888. This is not necessarily required to be known by the user, because for standard microservices, as the Jupyter notebook, you can just hit connect and you are here. But if you want to run more complex things, you can. And a perfect example is a remote desktop, which is served through a web interface. So what you see here on the right, it's a real software. It is AstroCook, which is also a poster in this conference. As you can see on the left, we have a container named AstroCook Desktop. On the right, on the details, we are using Sarusso, which is me, / AstroCook Desktop image. And this is triggered from Docker Hub as well. In this case, the port is 51530, which is pretty high. And this is because we are just assigning a random ephemeral port in the container itself of the microservice. The microservice exposes a web-based remote desktop client. You can just think about it as a VNC client. And then the connection is set back with the Science platform. And as a user, I can connect to the Science platform on port 7003, which is the port reserved to myself for this specific microservice.
Two-minute time check. Two-minute time check.
So this is how we can run microservices with whatever we want in this approach. So wrapping up, the capabilities of this approach are actually a superset of the standard approach. Users can run whatever software they want, and the more power users they are, the more freedom they have with respect of security, of course. Containers make it safe to run custom software because you cannot escape a container that easily. And there are also huge improvements in terms of reproducibility, because once a user has a container which is known to give a specific result, it can, of course, always force the specific version of the container, and therefore do not fall in the dependency hell problem where someone updates a dependency and you get your computations completely wrong. So this is it. Before the questions, I wanted to show you a live demo. Can you see this screen now? Or you still see the presentation?
Yeah, I see the cat.
You see the cat. So this is kitten, because anyone loves kittens, of course. This is real. It's connected to the Science platform. This is how a remote desktop served through the web client looks like. And just to give you an idea, this is the latency. So as you see, it's pretty smooth. At least I here see it pretty smooth. Of course, you will have some more latency due to the video connection. And here, this is a Jupyter notebook, which is running inside the browser, inside the container. So we are doing a bit of inception here, right? We have a web browser using a remote desktop client, which is web-based, and inside the remote desktop, we open another browser. But if we have some software which is meant to be interactive data analysis, the interaction is pretty smooth. And this is because modern technologies are quite more powerful than the old remote desktop client approach. So if you have a connection, if you have an unstable connection and you lose the connectivity, everything is restored as you left it. And I'm going to close the talk here. So I close the window. Suppose that I lost connection. I reopen the window and everything is there because the microservice is still running. And this is the same as Jupyter web server. And that was supposed to be a very quick live demo because we had a bit more time. So I put them in at the very last minute. So thank you. If you have any questions, I'm of course here.
You get the extra applause for all the kittens that people loved it. I saw it in the comments. All right. Any questions. Arik is saying this is not exactly a question, but an FYI. This is pretty much how SciServer works, and we have indeed run VNC containers for users. And actually, since it was mentioned, I've worked with SciServer, and I noted that under certain circumstances, I felt like being in a Russian doll. I had to open something inside, and there was no good way, or extremely complicated, to do cut and paste from my parent desktop where I often have information. So that's also an FYI from my side.
Sure, I agree on these observations. Of course, the remote desktop is just an example. The point is that you can do whatever you want. You don't need to contact system administrators, integrate if you're a power user, or if you are just a user and you find a container that is prepared to do something that you want, like Docker container we saw before. There's a chance that you can just run it as it is. I tried to run Elasticsearch and it worked with the standard container. So the remote desktop is just something that we are testing. There are other things that, of course, use remote desktops like this one. The nice thing in this architecture to me is that you can do whatever you want. So you are free to use the remote desktop if you want, or a Jupyter notebook. Is not that you have to choose between the two.
Dave Shoup wants to know, your desktop example uses VNC?
They do use a remote, so they do use a VNC server and a web-based VNC client. So as a user, you just need a web browser to use that. But yes, the underlying technology is VNC.
Okay, Sarah Weissman likes to know, does your system support authentication and authorization for any kind of the backend microservices APIs, or is the assumption that all users with an account on the VNC have access to everything?
So since every microservice is separated, the authentication is up to the microservice or to the tunnel. If you have an account on the VNC, you have an account on your very own VNC container. So you cannot escape the container that easily. If you are talking about how do you protect connections, this can happen at microservice level or at tunnel level. If the connection is a simple HTTP connection, you can add authentication in the tunnel. If it is something more elaborated, like for example, you just want an SSH connection, then you need, of course, to know the password for the container that you're accessing to from the Science platform. I hope I answered.
Yeah. Tamash wants to know, oh, there's more from him. He's working on a similar idea to provide microservices, including numerical computations over a REST API. And he has a working prototype based on Docker Swarm and load balancers, but at the same time, everything can also be used locally. Do you think it would be worth to collaborate to define a standard for microservice definitions? My idea is that each software library can provide a standardized configuration file, which can be used to spawn a container with a defined set of functions and API.
I think that it's worth exploring everything. There's actually more from Tamash, I think.
I didn't know if I wanted to confuse you, but you can read it.
I mean, what we wanted to test and what we wanted to propose in architecture is that the user is running its very own container or microservice. Then you can elaborate and sophisticate everything. But if I'm developing a container, which is, I don't know, it's hosting my modified version of Jupyter, for example, because I just wanted to edit the web interface, I can do it. So it's the interface of this entire thing is that it's only what the user wants in the container. So the containers and the microservices are supposed to be, I mean, if you run it locally, it will behave exactly in the same way as if you run on the Science platform. And if you run on a web server, it will behave exactly the same. So I think that if you add integrations, you will start losing this kind of modularity. But of course, it's worth to explore ways of collaborate with all the projects which are born in these years, I think.
Yeah, there was a question also on Discord. If you have concerns about scalability of the microservices.
Not at all. We are using microservices on a Slurm cluster at INAF. It's just a different way of running workloads. So it depends on how you schedule the microservices around your computing infrastructure. But one of the nice things here is that you don't really need you don't have any bottleneck because the only thing that your science platform is doing is tunneling the connection. That's the only possible bottleneck you have. All the other things are running separately and the users are using them separately. So personally, I'm not concerned about scalability. It's linear. We are testing how to run this kind of microservices with MPI. And this is still an open issue.
All right, thank you, Stefano.